In this example, we'd like to compute the surface area of a surface given by this parametric function. So I'm not going to sketch the exact surface the way it should be here, but maybe it looks something like this. And again, I'm very tersely sketching everything here because it doesn't really matter, okay? But the idea here is that the domain goes from just 0 to 1 in the u direction and 0 up to 2 in the v direction. And our domain domain D that we're going to integrate over is just a rectangle over here, and our vector function, our parametrization, maps this entire domain to this surface over here, okay, somehow. That's all we care about, and we want to compute the surface area of this thing. Alright, so let's recall that the surface area of a parametric surface S is given by the double integral over the parameter domain D of the length of the normal vector dA. All right, and the key here is that our normal vector is given by the cross product of the partial derivatives that build the tangent plane to the surface at every point. And so this is exactly what we need to compute. In this example, we're given the parametrization, so a lot of the work is done for us. We just need to actually do the computation, okay? We're even given the domain, right? So in this one, it's like, okay, a lot of stuff is given to us, so we're happy. We just need to compute all this stuff. So let's do it. I'm going to rewrite the vector function down here. Our vector r is u squared, uv in the second component, 1/2 v squared in the third component. We need to compute the partial derivative. So r sub u is 2u v and then 0. R sub v is 0, okay, u and then just 1v, just v. And we need to take the cross product of these. So I'm just going to do it from staring at this right here. So the cross product is going to be v squared minus 0, so v squared. The second component is going to be 0 minus 2uv, so minus 2uv. And then the third component is going to be 2u squared minus 0, so 2u squared. And we need to compute the length of this thing. So the length, by the way, this is our vector nu, right? And so the length of nu is going to be the sum, let's do squared first, the sum of the squares. So v to the fourth plus 4u squared v squared plus 4u to the fourth. Okay, and so this should factor to be v squared plus 2u squared. So v squared plus 2u squared quantity squared. We should check this, right? So you can multiply this out. V squared squared, check. V squared times 2u squared times 2, check. 2u squared squared, check. So this is correct, okay? And what this means then is that our area element that we're going to have to integrate up is just the length of this, the square root of this thing, which is just v squared plus 2u squared. And so this becomes our integrand of our integral. Remember the boundaries where u goes from 0 to 1 and v goes from 0 to 2. So our area is now very simply just the integral of v squared plus 2u squared du dv, inner integral from 0 to 1, outer from 0 to 2. All that we have left to do is compute this. Okay? And so let's do it. This is integral from 0 to 2. Antiderivatives of these with respect to their with respect to u for each of them, right, is just uv squared plus 2/3 u cubed from 0 to 1. And this becomes, what, when we plug in 1, this just leaves us with v squared plus 2/3. And then we have to integrate that dv. And so this is going to be, I'm going to do the integral. This becomes 1/3 v cubed plus 2/3 v, plug in 0 and 2, and we add this all up. We have 8/3 plus 4/3 minus 0 minus 0. This is 12/3, which is 4. And so the surface area of this surface is 4 square units.